I quite vividly remember my first time that I came in a laboratory where they did ecotoxicological testing. So they had this sort of huge laboratory bench, and there were lots of different jars on it, and each jar contained a DAFNIT, or a few DAFNITs, and lots of different concentration ranges. And I was looking at this, and this person was showing me around, saying, yes, so this is what we do. And I'm like, so you're implying that our whole line of reasoning in terms of how we think of environmental management is based on your desk? And he was, yes. And I was like, really? And I never got over the shock. So, ecotoxicological testing. Let's say we do a test with bees. This actual photograph was taken in our laboratory at CEH in the UK. Different pesticides tested for bees, different mixtures of metals and pesticide, different mixtures of pesticides. So again, it looks a bit similar to the DAFNITs. To do this test, you need lots of bees. And what you do is concentration ranges, lots of replicates. You could look at mixtures, in this case we did. Typical endpoints, growth, reproduction, survival. This point we also only looked at survival. Typically a bee, when it starts operating, it doesn't grow anymore, and most of them don't really reproduce. These tests are highly standardized. Typical day-night rhythm, temperature, everything, exposure time, so the duration of the test. Everything is highly standardized. And the end result will typically be something like an EC50 for growth or growth rate, an EC50 for reproduction or reproduction rate, LC50 for survival, and even up until now, NOECs and LOECs, despite the ban from OECD. And if you look at the mixture test, you can have some kind of additive effect compared to some kind of standard model. You can have synergistic effects where the toxicants enhance each other's toxicity. You can also find something like a dose level dependent interaction. So all kinds of details in the reaction pattern can be analyzed and can be found. So now if we look at the real world, this is a really nasty picture taken somewhere in America, some spill of something, and it killed a lot of fish. Another picture taken at the going down of Deepwater Horizon in the Mexican Gulf. I love the picture, but of course these people in their small boat with the vast scale of everything happening, they're completely without a chance of making any sort of difference. Still, good that they're there. This is taken somewhere in the Netherlands, on a much smaller scale, some fish. But still, we have this ecotoxicological test, and we have this real life things that we try to understand. And typically for Deepwater Horizon, everybody was sort of shaking their heads, yes, we should have an answer to this, but we don't really have an answer to this. So if you look at an ecotoxicological test, what type of question did you finally answer? And I think it's, if you look at the B test, so what is the effect of constant exposure to this mixture, to this species, to this endpoint, after 4 days, under standard OECD test conditions. So this is your sort of starting material, but your problem is on a much different scale. And I think the problem is in what is the effect of this mixture to this species. And it would be better if we ask a different question. And the different question would be, why do we see this effect? And if you have a better understanding of why you see this effect, you have a much bigger extrapolation potential. You can keep on doing these mixture tests forever. Copper and zinc, cadmium and lead. Well, you can go out to the periodic system and be in your laboratory forever, and this won't tell you a thing. So at some point, if you know something about cadmium and zinc, perhaps you could try to put this in a different framework and make predictions on species you haven't tested, or make predictions on compounds you haven't tested, or make predictions on mixtures you haven't tested. So if you start asking these more why-related questions, you start slicing the problem from a very different angle. And I think an angle with this much better extrapolation potential. So what are the processes by which toxicants affect organisms, and how can we use this knowledge to come from a laboratory test to understanding something in the real world? It's also a bit strange that you do a test, let's say for a Daphnia, or for a fish, doesn't really matter. You look at different endpoints, at growth, at reproduction, you could look at respiration, typically you also look at survival. This is one species. So how come you end up with 4 different answers, or 5 different answers, or 6 different answers? It's one species, and you affect this one species. And these things must be linked in some way. In the end, it's one species. And this is where depth theory could step in. All these different endpoints are basically linked through energy. If a species doesn't eat, it won't reproduce. If it doesn't reproduce, or if it doesn't grow, it won't reproduce. So these things are interlinked, and the framework of the dynamic energy budget theory at least gives a natural framework. It's tested, it's well documented, that allows integrating these different endpoints. So it's conserved, it's got conservation of time, energy and mass. And it has the potential to link different levels of organization. So it starts from the individual, you can look deeper down in the individual, and you can also start looking at the individual and try to look up in populations or ecosystems. For me, the following 4 pictures were very influencing my whole line of reasoning. This is a Daphnia. It's growing. It's after some 4 days it starts to produce offspring, and at that point it's about 2 millimeters. And if you look at oxygen consumption, and if you look at ingestion rate, it's still all smooth transitions. There is no sudden hiccups in the curve. It's all smooth. It just goes on. But this is striking if you realize that this daphnid is able to produce offspring at a very high percentage of its own body weight, up to 50% if I'm correct. So it produces offspring, so there must be a huge energy drain. Still, you don't see anything happening in these curves. It's all smooth, it's all going on, it's just continue sort of living. And so try to, thank you. Try to put a mechanism behind this. And basically this is a depth organism. So it takes up food from its environment, converts this food in reserves, and you can use the reserves to grow, to mature, and to produce offspring. And we already spoke about this kappa rule. Well, here it is. So a fraction of the reserves goes to structure, and the remaining bit goes to maturity and producing offspring. So there is no competition between growth and producing offspring, it's all fueled from the same source. So if you look at the scheme, then a toxicant can affect the different processes. So it can affect the cost for growth, it can affect the cost for assimilation, it can pose a hazard to the embryo. So within this framework, you have a very different concept of mode of action. And this is not just something you dream up and you look out the window for some time and you think, well, this is how the world works. You can actually see this back in actual measurements. So this is an example for the cost of maintenance with Paulsomia candida, a small soil-dwelling insect, exposed to triphenyl tin. So its body length is, its growth is hampered by the toxicant, and its cumulative offspring is quite badly influenced by the toxicant. You can also affect maintenance. Basically, you see a different pattern emerging. So the species will grow to the same final length, only it will take longer because it needs more time to generate the same type of energy. And again, the cumulative offspring is impaired. And the final example that I'm going to show is for embryo hazard. In this case, the parent just lives on as if nothing is happening, but the amount of offspring is really badly impaired. So these sort of modes of action that you just derive from looking at your scheme on how your species works are things you can actually see in real life. And if you look at this from this way, then it makes sense that food limitation has an effect on an ecotoxicological test in itself. And it's very difficult to find these things out without a framework like this. I will give some examples of applications on effects of mixtures. I stick to survival because this is by far the easiest way to proceed, and especially if you work with really complex mixtures. The first example is the same organism, again exposed to a mixture of two metals. And the basic question here was, do compounds work together? And I think the answer is yes. And this gives a very good idea on what this model does. So over here we have time going. The net-like structure basically is the prediction of the model, and the bars are the actual measured effects on the survival of these species. And well, over here it's going extinct really rapidly, and over here it takes more time, so it's a mixture of copper and cadmium. And we also came to the conclusion that there is no interactions in this system. Over here you have the basically control mortality, so this goes down sort of slowly over time, and at some point you sort of fall off your control mortality, and this is your no effect concentration, and then basically your survival probability will be affected by the toxicant. If I talk to my colleagues on interpretations of this type of modeling, then typically they say, well, this is very interesting, we will agree on that it's quite powerful, but we have to do more work in the lab. And we don't always like this. And well, so does depth modeling require extensive data? Well, you do need data over time. It's a time-specific model, and anything like an LC50 is just a snapshot in time, and basically you don't have a clue on what you're actually doing. It's just that snapshot over time. 48 hours later, it can be completely different. Order of magnitude easy. 24 hours before, it will be completely different, but you just don't know. So it's very tricky to base your risk assessment on a snapshot where you don't have a clue on where the snapshot is actually taken. So I think it depends on your question, and I would even go one step further. Any question that can be answered by performing a standardized OECD test is likely not to be very interesting from a scientific point of view. So the message here is basically use these models, use all available knowledge that you can gather. Look at literature, use QSARs, the whole lot. And this can really reduce your experimental effort quite considerably. And so it's not only something that puts you up with more work, it can really take away a lot of work. And I'll show an example of this after this example. This is something that really triggered me to go back to research, and I got the opportunity from Bas some time ago. So this is an area at Westland. If you zoom in, you can see the greenhouses emerging. It's about, I don't know, like 10 by 10 kilometers, so in total 100 square kilometers. About 50% of the total surface area there is covered with greenhouses. It's just south of the city The Hague, for those who are familiar with the Netherlands. And these greenhouses produce a lot of pollution. Let's phrase it like this. So a number of the pesticides go out. These greenhouses, the structure is made from zinc-coated steel. So there's a lot of zinc in the water bodies. Typically quite high concentrations of copper. So around 1990, the Delftland Water Board, who still is responsible for the surface water quality in this area, said, well, we don't think that just going out, taking samples, looking what's in there, will give a real representation of what's actually going on in terms of environmental quality. So they have a number of different sampling sites through this area. The general idea is to follow, to start with clean water and just follow sort of the pollution in there, and then at some point it will be somebody else's problem, and that's where they stop measuring. So next to the real chemical measurements, comprising of, I don't know, something like 35 different pesticides, 10 heavy metals, 10 PAH, a number of PCBs, nutrients, salts. So basically the whole periodic system of pollution can be found there, and typically in rather high concentrations. So they added 6 measurements of DAFNITs per year per site. And this is where they are working with these DAFNITs. So they put the DAFNITs in a jar, expose them, there is free exchange of water, and after 8 days of exposure they come back, try to find back their jars, and then look at survival of these DAFNITs. And from here you can see, well, this is, I don't know, like 1.5 meters deep, and the other one would be, I don't know, this deep. So very different water bodies is what they are looking in. This model, and basically using only available data from literature, the Ecotox database was very important for us. We were able to find all the parameters we need to build the model. We looked at this no effect concentration of the mixture for metals, for the pesticides, for the nutrients, for the salts taken separately, and then looked at which one of the no effect concentrations of the mixture was exceeded, and this tells you which of the compounds is responsible for the observation of the population of daphnids going extinct or not. Well, typically it's single compounds, and in one case it was the combination of pesticides that really made sure the daphnids would go extinct. So it's not one of the pesticides, all of the pesticides combined exceeded the threshold level. Something that we also learned from this exercise is a surface water could comply to any regulatory standard, and still the mixture effects and typically of the metals could be such that this daphnid population could go extinct within 24 hours. So mixtures are not really regulated. So with this model we could make these predictions, we could make use of readily available data, and other approaches just failed. We were looking at the effect of PAHs, mixtures of PAHs. This is a measurement that was done in the laboratory of VU at Kees van Gestel. Mieke Broers did the measurements. And basically we had data on a mixture of PAH and of one single PAH. And we derived the toxicity parameters using QSARs from this one PAH for these other two, and then used the toxicity parameters to calculate the mixture effect. And as you can see, it's almost spot on. And it's the whole time course of the toxicity that can be predicted for a mixture of 3 components by just doing one measurement. So it's not necessarily true that you need more data. The final example, this is something that was done quite recently. We already sort of came across the @mypet database. I will tell a little bit more about this. So the use of depth theory in understanding species sensitivity. I think understanding species sensitivity is one of the key things that we are discussing now, today. And predicting species sensitivity is, I think, as close as you can get to the holy grail of ecotoxicology. So people tried, and over time, better or less better efforts were made. I think somewhere in the 90s it was quite popular to do research on this, and it sort of faded away, and for the past few years it's sort of starting to emerge again. Some traits that people related to sensitivity of species and that are mentioned in literature are size, armor, feeding type, mode of respiration, life cycle duration, and something that I found quite interesting that's not here is the elaborateness of the nervous system. And something that was mentioned several times is metabolism. But no one, for I don't know reasons, tried, and we did. So you have to think about some compounds. You need compounds where you have toxicity data available for a lot of different species. So we came up with pesticides. Again, use the Ecotox database and look for species. And we wanted pesticides with metabolic activation and 2 pesticides without metabolic activation to sort of see if it's the metabolism itself or if it's the metabolic trickery that can cause the effects. So, of course, you need data. For the species sensitivity, we use the US EPA Ecotox database, and we were able to derive no effect concentrations for each of the compounds between, 15 and 30, 35 different species. And for metabolism, we used the @mypet database. Basically, this is a list of species, 411, I heard a few hours before. So it's 411 species, And for each species, typical life cycle parameters are gathered. So maximum length, how old do they get, when do they start reproducing, a number of other life cycle parameters. From these parameters, using this depth model, you can derive depth parameters. And one of these parameters is the specific somatic maintenance rate. When I wrote this, it was some 400 species. I think it was 398. So 13 have emerged. It's mammals, birds, reptiles. So for any major class of species, it's in there. These life cycle data that I refer to, time to hatching, weight at birth, weight at puberty. So just standard life cycle data that are converted to depth parameters, and one of these is the specific somatic maintenance rate. And typically for fish it's in the order of 20, but the highest value that we found in this database is about 8,000. And basically this is the amount of energy that an organism needs to keep 1 cubic centimeter of itself going for 1 day. So we expressed the sensitivity as having a low toxicological threshold for survival, or a low no effect concentration, and we used these different values for the maintenance rate to see what comes out. And basically this is what comes out. So it's the different compounds. Basically you see exactly the same. The higher the specific somatic maintenance rate, the more sensitive the species gets, which in sort of intuitive makes sense. If you have something that's just lurking on the floor of, I don't know, some sea, and occasionally catches something and then it's gone for several months with very low metabolism, it's very difficult to interfere with it. But if it's got high turnover, active, it's much more easy to interfere. So that was the underlying assumption, and I think we showed that this works, at least for these compounds. I put this in a species sensitivity distribution. We already saw 2, I think, earlier today. I think the nice thing is I did something that you basically can't do, make a species sensitivity distribution based on this specific somatic maintenance rate. And then you basically find the same distribution, but the more interesting thing is that the order of the species is almost spot on the same for the sensitivity as it is for this specific somatic maintenance rate. And you can do this for all 4 compounds and come to the same conclusion. What we learned from this, at least for these compounds, this specific somatic maintenance rate does influence species sensitivity. Something that was mentioned quite a lot in literature was size as a driver for species sensitivity, and we think it's not. So we think that typically these smaller species have a higher metabolism, and it's the metabolism that is the driving force, and it's not the size itself. But if you look at these databases, and we depend on databases, they are biased towards species with a short lifespan and high turnover, because they're much easier to culture. So high offspring, short life cycles, so very, very convenient to do your tests with them. If you now feel like this, I did something wrong.